So if we can shift up or down, we can shift left or right, then how do reflections occur? Because we've already seen examples of functions that exhibit y-axis and origin symmetry. We've also seen graphs that exhibit x-axis symmetry. So the question is, how can we recognize this symmetry in a graph, but algebraically? Well, it turns out that the answer is negatives. So, for example, we can look at f of x equals the square root of x. This is a parent function. We should know what it looks like. Right off the bat, you should say, oh, look, it looks like this. And now what we're going to do is we're going to graph two options. G of x equals negative square root, and h of x equals the square root of negative x. So let's take a look. And I'm actually going to do this in two different tables. We're going to do x and g of x. And we're going to have a separate table for x and h of x. And there's a reason for that. Look at g. G is just the negative square root. Note that when I graph g, I cannot choose x values that are negative, because then the inside of this root would be negative, and I can't take the square root of a negative. So I can't pick negative 2 here, for example. But what I can pick are positive values. So note, if I try to do, say, negative 2, negative 1, 0, 1, and 2, negative 2 and negative 1 will not work because I can't square root a negative. But if I evaluate g at 0, I'm going to get the negative square root of 0, which is 0. For 1, I'll get negative square root of 1, which is negative 1. And for 2, I'll get negative, well, let's, instead of using 2, let's use, say, 4, because it's easier to square root. So we'll do negative square root of 4, which is a negative 2. Now, this is a good point to pause and have a small commentary. If we go all the way back to our parent functions, we go back to our square root, you may say, wait a minute. When I square root a function, don't I get a positive and a negative? And the answer is yes. However, that's only true when you're solving an equation, not graphing. So if I give you an equation and say solve for x, and you have to square root somewhere, then you'll admit the positive and the negative. But when we graph the square root function, we're only talking about the positive outputs. So it's a small point to make, but an important distinction. So here I have g, and then let's take a look at h here. So look at h. H is the square root of negative x. So if I were to try to put in similar values, let's try negative 4, negative 1, 0, 1, and 4. Observe that negative 4 is now a valid input. So we'll do the square root of negative negative 4. That's the square root of positive 4, which is 2. The square root of negative negative 1 will give me the square root of 1, which is 1. The square root of negative 0 is just the square root of 0, which is 0. And now it's the positive inputs that are going to give me trouble. So here I'm going to have, for example, I'm going to try to do the square root of negative 1. This won't work at all. For the same reason, these inputs don't work. The domain doesn't allow negative inputs. So let's graph what we can. Let's graph g of x first. We plot the points 0, 0, 1, negative 1, and then 4, 2. Play connect the dots, and it looks like this. This is g. It looks like we've exhibited x-axis symmetry. So g of x is f of x reflected about the x-axis. So when we take f, which is square root of x, and we multiply a negative on the outside, it seems like we get x-axis symmetry. But look at h. H, we multiplied by x negative on the inside. So if I graph that, I'm going to get negative 4, 2, negative 1, 1, and 0, 0. So there, when I connect the dots, it would look something like this. And we see that this object, h of x, this is f of x, but it's been reflected around the y-axis. So this is reflected about the y-axis. And we see there h of x had negative multiplied on the inside. So generally speaking, we have the following. If you're given a function f of x, then you see a g whose graph is exactly f's but reflected about the y-axis, then we see it's much like this h. We see that we must have multiplied by a negative on the inside. So therefore g of x must be equal to, say, f of negative x. Whereas if your g has a graph that is reflected around the x-axis, then that is a lot like this g right here, which is exhibiting x-axis reflections. So therefore, here we notice g, we multiplied by negative on the outside. So that's exactly what we have here, negative f of x. And so what we see is that we can vertically shift up or down, horizontally shift left or right. We can now induce reflections by throwing in some negatives. And there's one last thing we can do to our functions, and that's stretch and shrink. This idea allows us to squish or stretch a given parent function to make it look sort of how we want it to look. And the best way to represent that is by examples. So what we have is f of x equals x squared. That's this unadulterated standard quadratic on the left. And what we see is the following. If I multiply by a constant, so notice that here I've multiplied by a constant that's larger than 1. So here I've multiplied f of x by the constant 2, parentheses, which is bigger than 1. If I do that, this is going to induce a vertical stretch. That's what this is inducing. So what you see is that if I took this smiley face and I were to stretch it all the way up vertically, it would look a little bit like this stretched smiley face. So this is inducing a vertical stretch. And equivalently, if I were to instead take my smiley face and multiply by a constant that's less than 1. So here, I multiplied, it's the exact same observation, except now I multiplied by not 2, but 1/2, which is less than 1. And you can see it has the opposite impact. I've taken my smiley face and I squished it or compressed it vertically. So this is what we call a vertical compression. All of this business is about multiplying the whole entire function by a constant. And this induces vertical stretching and shrinking. But just like with vertical translations or shifting, if instead I multiply not the all of f, but I multiply the inside of f by a constant, it will have an effect not on vertical stretching or compression, but instead on horizontal stretching or compressing. And so we can look at an example. Here I'm going to take f of x equals x squared, and now I'm going to multiply the inside by 2. So if I do that, here I've multiplied not f of x, but I've multiplied x. This is the inside by 2, which is greater than 1. Let's see what happens. Instead, let's see, when I plug in, say, 2, plug in 2, I get 2 times 2 is 4, 4 squared, 16. Whoa, that's really, really, really big. Let's plug in a better number. Let's plug in 1. 1 times 2 is 2. 2 squared is 4. Wow, we're already all the way up here. And so similarly for -1, we're up here. And for 0, we're at 0. So this function looks like this. What you'll see is that this is inducing, it looks like a vertical stretch, much like this one. But when you multiply on the inside, you need to think horizontally. And so if you look at this object, this graph, it looks like the original smiley face, except instead, if you think about it, you put one hand over here and one hand over here, and you were to push inward, it looks like this object has been squished horizontally. So this is resulting in what's known as a horizontal compression. And you'll notice here the constant is greater than 1. In the vertical case, being greater than 1 was a stretch. But just like for the shifting, when you flip to a horizontal viewpoint, it's the opposite. So a constant greater than 1 that would have been a stretch vertically becomes a compression horizontally. And similarly, if I were to come through and I were to multiply by 1/2 on the inside, which is a constant less than 1, so we're multiplying the inside by 1/2, instead of being a horizontal compression, you can think of this as a horizontal stretch. So for example, if I were to evaluate this at 4, 4 over 2 is 2, 2 squared is 4. So if this is 4, I know 4 4s on that, 4 4. This becomes my graph. And so this is a stretch horizontally. And so this is going to be a horizontal stretch. Now, in all actuality, this is a lot of information. And in some sense, it's a little redundant, because what if we graphed this function? This function, we're multiplying on the outside by a 4, so that tells me it's a vertical stretch because I'm multiplying the outside by 4. So this is a vertical stretch. Vertical stretch. By a factor of 4, you can plot in some values. Let's put in, say, -1. -1 squared is 1 times 4 is 4. And if I put in a 1, we also get a 4. And so this will look something like this. And now you may get frustrated, because you'll say, wait, this graph is identical to this graph. And I would say, yes, of course it is, because 4x squared is the same as 2x, quantity squared, algebraically. And then you may say, wait a minute, how can this be a vertical stretch, but this be a horizontal compression? And the answer is, they can be both at the same time. Vertical stretches are horizontal compressions, but by different factors. This is a vertical stretch by a factor of 4. This is a horizontal compression by a factor of 2. And they are equivalent up to whatever function you're working with. Here it's the square. And so when this 2 comes out of the square, it comes out as a 4. and it converts your horizontal compression into a vertical stretch. So a lot of this stuff is the same exact knowledge, just packaged in different ways. Okay, so far we've talked about a lot. We talked about, in the beginning, parent functions. These are our building blocks. And then we moved forward and we learned about how we can take any parent function and we can vertically shift it up or down. And then we said, okay, can we shift left to right? Yes. And then we said, can you reflect? Yes. And then can you stretch or shrink? And the answer is yes. So if you know all of these like the back of your hand, which you should eventually, and the better you are at knowing this information, the far more successful you'll be in your future mathematical scientific endeavors, then you can tie them all together in one fell swoop. For example, this is a question you can tackle based on our conversation. And so, for example, you can combine them together. Sometimes you'll look at functions that look like this. This function is complicated looking, but at its core, it is effectively this function, x squared, but with some transformations. It looks like I've taken x squared, I subtracted 1 on the inside, I then multiplied by -2 on the outside, and then I added a 3. And that got me this function. But each of those algebraic moves have a graphical effect. And so as a result, if you want to graph g, which is our objective, we can start with the parent function, something you've memorized, and then slowly but surely trace what transformations it's undergone algebraically, and then trace those out graphically. In this manner, order matters. You have to sort of read it in an inside-out manner. I like to pretend this function that we're given is some sort of a setting, and that this square, the parent function, is your house. And so if you were to live right here inside of the square function, and you were to wake up on a given day, the question is, what would you encounter first? The first thing I would encounter is this -1. Well, a -1 on the inside of your parent function results in a horizontal shift. That's a shift 1 unit right. Remember, it's opposite of the sign. Then, when you leave your house, the square, the next thing you encounter is this 2. A multiplication of your entire function by a factor 2, which is greater than 1, results in a vertical stretch by a factor of 2. The next thing you notice is this negative, and a negative on the outside of your entire function results in an x-axis reflection. And then finally, what you notice is you see this +3. And this adding of 3 to the entire function results in a vertical shift of 3 units. And then finally, when you undergo all of those, you build your overall function g. One thing to pay attention to is that order matters. You have to do it in this order. Yes, some steps are interchangeable, but largely speaking, if you follow this order, you'll never have a problem. So let's take a look at how we can graph something like this. We're going to graph this sequence. And the way I want you to write it is I want you to actually write out these steps on the up here, and I want you to number them and graph each step. So you'd rewrite these steps, and then as you number them, we're going to start shifting this smiley face. So, 1, the first step, we have f of x equals, well, you know, we can skip the f of x part if you want to just call it x squared. Then we're going to shift it 1 unit to the right, and that's step 2. So we're going to come here, I'm going to use a different color. We're going to go over here 2 units to the right, and then we're going to draw our smiley face. We're going to label that step 2. Then I'm going to use a different color, and we're going to do step 3. Step 3 says vertically stretch by a factor of 2. So that's going to pull everything upward. And so a sketch of that might look something like this. And this might be step 3. Next step, it looks like we want to reflect about the x-axis. So if this is the x-axis, we reflect about it, that number 3, and it might look something like this. This is step 4. And then finally, step 5 says shift 3 units up. And so we'll graph that maybe in green. And if we go a couple of units up, we might call this 3. We shift red, the red graph, 3 units up, and it might look something like this. And that's step 5. And if you follow the sequence of steps, then this last option is always going to be our function g of x, which is negative 2 times x minus 1 squared plus 3. And so in this manner, we can now graph any sort of crazy looking function like this. It amounts to taking your parent function and then carefully tracing out all of the steps, the parent function transformation steps, that yield your new function. And then taking these algebraic observations and converting them into their graphical representations. Tracing those out, and that gets your final answer. When you're tasked with doing this, either on the homework or in an exam, you should always write out an itemized list and then draw exactly what I have here. You draw many different functions, labeling them as you go, so that the reader understands what graph is representing what step in your process, and so that they know that the last step is the desired function. If you just go from step 1 to step 5 here, the reader is getting lost at how you did any of the intermediate work. This is the type of stuff that if you excel at learning and you get really good at this, you will find incredible success in all future math classes. I know I say that a lot, and of all the things we've covered so far, I'd have to say I mean it the most when I say it about this. To assist you in learning how to do this, we have more examples here. This one uses an x cubed function. The one we have down here uses a square root function. And so for this one, I might draw the itemized list and leave the graphing for you. And for this one, I'll leave the entire problem for you to tackle, so you can do it in the same way. For example 6, we have g of x equals this function. And again, the way I like to think of this is I think of it like you're living inside of the parent function, and all of a sudden tons of things change. And you want to start where you're living, which is in here in the parent function, and ask what changes first around you. And so step 1, you can start with a variety of options, but I like to start with the parent function. So step 1 is graph f of x equals x cubed. Step 2, we witness a minus 3 on the inside. Because it's on the inside of the parent function, I know it's going to be a horizontal change, and therefore it's going to be opposite of what you think. And so the negative 3 makes me think of 3 units to the left, but the opposite would be 3 units to the right. So step 2 is shift 3 units to the right to get x minus 3 cubed. The next thing I notice is this 1/2 on the outside. Since it's on the outside, that will induce a vertical stretch or compression. And since the 1/2 is less than 1, that's a vertical compression. So step 3 is compress vertically by a factor of 1/2 to get 1/2 x minus 3 cubed. And then finally, we have a minus 2 on the outside. Being on the outside, that'll induce a vertical shift up or down. Because it's a minus 2, that'll be a vertical shift downward. So step 4 is shift 2 units down to get, and now we're done. So we're going to write g of x equals 1/2 x minus 3 cubed minus 2. And so this is how you build an itemized list, labeling each step so that you can use those labels on your graphs to the right. Notice I said graphs plural because you're going to graph a different copy for every single iteration to the point where the final iteration is exactly the desired function. And so this is an example of how you might build this itemized list that here was given to you. So follow this step-by-step graphing procedure to build the overall graph on the right. And once you're comfortable with this example, feel free to tackle this last one as a way to practice this on your own as well. And so overall, this conversation allows us to unlock a wide variety of new functions. The 7 functions we started with were just the beginning. Those are the building blocks. And then through vertical stretching, compression, or vertical shifting up and down, horizontal shifting left and right, X or Y axis reflections, and then vertical stretching or compressing, horizontal stretching, compressing, you can take those building block parent functions and build a seemingly infinite number of possibilities. Overall, we'll wrap up the conversation here. As always, if you have any questions, be sure to let me know. Otherwise, I'll catch you all next time.